Okay, so let us continue our lesson in Math 5. So, about set theory. So, if you remember, I described some operations on sets for you. One of them is not probably called operation, or I don't know, because if I have a set, I define the complement of that set for you. So, what was the definition of complement? It was the set consisting of all elements in the universal set so that that element does not belong to the set itself. I don't know if it's a good idea to call it an operation. Yeah, might be, because I give a function in, I give it a set in, it gives me another set back, okay? It's an operation somehow, but the input is just one set. But I also have operations between two sets. One of them was called union, if you remember, A union B. This is the set consisting of all elements from the universal set, so that that element is either in A or in B. Or of course, in mathematics, when we say or, it is always an inclusive or. So either this one, not that one, this one, not this one, or both. So when we say or, it's different from the normal language that we usually speak. Usually when we say or, it means either this one, not that one, or the other way around. But in mathematics, always, if it is not mentioned, it is an inclusive or. And the symbol for exclusive or is this one. Okay. Okay, but let us not deviate that much. And then I had also introduced you another operation. This is the intersection. So this is the set consisting of all elements in the universal set. So it is so that those elements are in both of them simultaneously. So this becomes AND now. So we discussed about them. We also learned some properties of them. For example, we learned that these operations are commutative. There is no difference between A union B and B union A, the same for this one. We also, for example, learned that A union A itself is the set itself, the same for intersection. We learned about associativity. We learned about distributivity. We also learned about the absorption laws. We also learned about De Morgan laws. Do you remember? What was De Morgan laws? What are De Morgan laws? If I have A union B complement, it becomes A complement B complement, but intersection. And we also have A intersection B complement, it becomes A complement union B complement. These are expressed in your book, but not under the title of some rules that you have to have them in memory. But that is very fun because these are very fundamental rules in set theory. These are called De Morgan laws. De Morgan laws, yes. Anyway, we want to introduce one more operation, and that is a difference of two sets. So I usually denote it by A minus B, the difference. But because might be some students get confused of this minus sign here, it is also very common, and it is the same in your book, they denote it by this symbol. So this is called set theoretic difference, this symbol, okay? But anyway, in your book, you are using this notation, but I will follow this simple notation, okay? But how should I define that? The definition is also very simple. When I write A minus B, if A and B are two given sets, this means the set consisting of all x's that of course are coming from the universal set. But how? So that this x belongs to the first one and it does not belong to the second one. This is called this is the set A minus B. Yes, is that clear? So when I want to write A minus B, and immediately it becomes clear, it is asymmetric with respect to A and B. Because here x belongs to A. A is the first one here, but x does not belong to the second one. So it should be a priori clear to you that A minus B should be different from B minus A in general. Okay? So it is not commutative. But let me give you a very simple example first. So let me give you two sets. A is, let us say, A, B, C, and D. And let me give you B to be X, Y, Z, U, A, B, and T. If I ask you what is A minus B, it means it is the set consisting of all elements that are in A, with an extra condition that those elements are not in B. So A is in A, but it is also in B. So I am not allowed to include it here. Okay? So A will not find its way here. What about B? B is in set A. Okay, am I allowed to put it down? Before putting it down, I have to check if it is here or not. I see that yes, it is also there, so I don't bring it down. Yes? But what about C? C is an element which is in A on the one hand, and it is not in B on the other hand. So yes, I am allowed to bring it down. And the D, should I bring D down as well? Yes, because D is in A, but not in B. So this is end of story. I don't know why some students also include the other way around. Be careful, that is not the case. I am only interested in all elements from the first one that are not in the second one. That's it. Yes? Okay. What about B minus A? B minus A is the set consisting of all elements in the first set, in this case the first set is B, which are not in the second set. The second set in this case is A. So it means that I look into the elements of B. The first one is X, is in B. It is not in A, so I am allowed to bring it down. Y is in B, not in A, I am allowed to bring it down. Z is in B, not in A, I am allowed to bring it down. The same for U. But A not only belongs to B, but also to A, so I'm not allowed to bring it down. The same for B, I'm not allowed to bring it down, but T, I bring it down. So that is set A minus B. That is set B minus A. Is that clear? Okay. So for example, let me give you another example. If A is 1 and 2, and B is 1 and 2 and 3. So what is A minus B? All elements that are in A but not in B. So you open the curly brackets, you are looking for elements in A that are not in B. Can you find such an element? No. You cannot find, so you close it. What is the meaning of this? It is the empty set. So A minus B is the empty set. But what is B minus A? You open the curly brackets, you look into B elements and choose the ones that are not in A. There is only one with that property, and that is 3, and then you close it. Okay? So let me ask you one question. How much do you agree with this? Not in this case. I pick two sets in my head, A and B, and I write this on the board. You don't know the sets that I have chosen. But can you be confident this is true? Yes or no? Because I told you A minus B means what? Means you go and choose those elements of A that are not in B. So in principle, you are choosing either all elements of A or a portion of elements of A. Okay, so that is definitely a subset of A. Is it true if I write B minus A is a subset of B? Yes. Yes, that's clear. So let us try to understand the concept a little bit better. So what do you think? Again, I am talking in general, not for these examples. Forget about A and B. Just typical sets A and B. What can I write about this? The empty set. Is that understandable? So if I have a set and subtract the set itself from it, it should be the empty set. What do you think will happen here? The universal set minus the set A. The complement of A. Yes, because it means all elements in the universal set that are not in this set. It means A complement. What do you think will happen here? A minus this. A minus the universal set. It is all elements which are in the first set but not in the second set. Can I find such an element by the definition of the universal set? No. So what is this one? Empty. Okay? I don't know. What do you think about this? A minus the empty set. It's the set itself. The empty set minus a set. The empty set again. Yes, understandable? Okay, let us try to understand the situation using the Venn diagram. It's an extremely important tool in our hand to visualize set algebra. Okay, so let us try to draw a Venn diagram for a typical shape. For example, if this is my universal set, let me take the most general case that A and B are like this. If I want to color A minus B for you, where should I color? Those area, that region, which is within A, but not in B. So what is left? This part is left. Do you agree?
Yes.
Okay, so this is A minus B. What about this scenario? Might be I have this scenario. Do you remember what was the name of these? What was the terminology here? If I have this situation for my set in A and B, there was a disjoint. So if two sets don't overlap at all, those are called disjoint sets. If my sets are disjoint, where should I color for A minus B? The entire A. Yes? So this is an example. For example, if A is 2 and 3, B is 4 and 5. If I ask you what is A minus B, is A itself. If I ask you what is B minus A, is B itself. Okay? This is this scenario for this case. I don't know, might be I have this scenario. So where is A minus B? It is outside B, within A. So this becomes this ring. So this part is A minus B again. If it was the other way around, of course, you understand what should be. So if this is B, this is A. What is A minus B in this case? The empty set. Okay, so these are some good pictures. But there is one important rule. This is in the book as an exercise, but I want you to remember it at least for this lesson so that we can have a little bit of fun. The theorem is this. I can call it a theorem, but this is not the way that the book mentions that. You know, we can get rid of the subtraction sign in favor of complementation, in favor of taking complement and subtraction. Taking complement and intersection. So the formula is this. So A minus B can always be written as A intersection with B complement. Okay? Before doing, let us try to understand it from Venn diagram point of view and then prove it rigorously. And then, of course, we can explore some of interesting consequences of this. Okay, from the Venn diagram point of view, how can I convince myself that this is always true? Of course, using Venn diagram, I cannot convince myself this is always true, but I can understand intuitively why this might be true. And then, because this is equality, I need two identical diagrams. Drawing identical diagrams with hand is not an easy task, but let us imagine, or let us better pretend that these are identical. Okay. On one diagram, I highlight A minus B. On the other diagram, I highlight A intersection B complement. And then we compare them. By the way, let me make sure that you understand that one. So this complement is affecting only B. Okay, so if I want to calculate this intersection, what should I do? I have to find the complement of B first and then intersection. So the priority is with this operation taking complements. If I want to put the complement after intersection, I have to use pair of brackets. So this means that first I intersect, then I complement, but this I have to complement only B and then take the intersection. So be careful about this. So the priority is with that operation. Okay, so now here, A minus B is extremely simple. So A minus B is exactly as this picture we have. This is the left side. This is A minus B. But now for A intersection B complement, I need to know where B complement is. B complement means outside B. So if you don't mind, let me just highlight the region with vertical lines. Oh, sorry, yes. Outside, okay, outside B. But it doesn't matter if I go within A. Yes, something like this, okay. And then this green part is B complement. And then I want to intersect it with A. Where is A? Of course, A is the whole circle of A. The whole circle of A. I want to find the overlap between the green region and region included within the circle A. Do you see where it is? Yes, it is exactly this. Do you agree? The overlap between the green region and the circle representing A is that region, which is exactly identical to this. So this one is, on the other hand, is this. So hopefully you are convinced. But let us do it rigorously. Okay, do you remember, if I want to prove two sets are equal, what should I show? This is always the case. If I give you two sets and I ask you, prove that they are equal, yes? Yes, yes. Every element on the left should be in the right and vice versa. Yes, so this is always true. So if I have two sets and I want to confirm this, I have two tasks to do. First, I have to show that the left side is a subset of the right side, and the right side is a subset of the left side. If I can show this together, it becomes A equals to B. And then, so I would write it like this. I would say that let X be an element in A minus B. We show that X also belongs to A intersection B complement, but that is not enough, and vice versa. Yes? Okay. I start from here. X belongs to A minus B. If someone guarantees that X belongs to the difference of these two sets, I am allowed to conclude what based on the definition of subtraction we just had. What can I write? X belongs to A, but we also have more information. And X does not belong to B. Let us not jump. Especially the proofs, let us not jump the steps. Okay, but now we can translate it again. X belongs to A is the same. But when X does not live in B, where does it live? In its complement, based on the definition of the complement. But what can I conclude? I have two sets, I don't know anything about them, but I know something. I know the X belongs to both of them. So definitely X belongs to where? In the overlap. X is in the overlap, so X belongs to the intersection. So one side is finished. The other side is also clear, but I'm so lazy to write it again, so let us just see that I can reverse the arrows. So, do you think I can go back in that direction here? If I pick an X which is inside this one, can I conclude this? Yes, because of the definition of overlap, intersection. If X belongs to the intersection, it should be in both of them. So this step is possible. Is this a step possible? The answer is yes. Yeah? Because X belongs to A is just copied and pasted. And if X belongs to B complement, it is guaranteed that X does not belong to B itself. And based on the definition of subtraction of two sets, that is also reversible. So I'm on the safe side. Okay? But what is the message behind the formula? So this formula tells you that if you have the difference of two sets, you can transform subtraction into intersection, but there is a price to pay. The price is to make the second one complement. Okay? Be careful about that, yes? But now can you tell me, for example, let us try to test your understanding here. For example, can you tell me what can I write for B minus A? B intersection A complement. Okay, let me ask you one more question. Can you write A intersection B in terms of subtraction? This is just a curiosity, because usually this is not useful. Usually the useful one is to transform subtraction into intersection. Why? Because we know a lot of rules for intersection. Commutativity, associativity, distributivity, De Morgan laws, a lot of laws. Yes? So getting rid of subtraction in favor of intersection is good, because I can use a lot of rules. But the other way around is not useful, usually, unless you insist to do something in the problem. But now my question for you is that, just for mathematical curiosity, can you write this intersection in the form of subtraction? Yes? Yes. So you are saying that it is A minus B complement. How many of you agree with that? Yes or no? Is that understandable? Is it correct? Yes. Yes. Because I go backward, I write the first one, I change this to intersection. The price that I have to pay is to make the second one complement. But the complement becomes this. But this is not the only way to do it. There's an alternative way to do it. Yes? I can write it a different way. What? I can simply write it as B minus A complement. Because this will give you B intersection A, but B intersection A and A intersection B are the same. So if I want to go from intersection to subtraction, I can do it in two different ways. Yes? Yes or no? Okay. So that is a very nice relation. So it means A minus B complement is B minus A complement. Yes? Yeah, I mean, I'm just exploring things, yes? If I ask you what is this, you would tell me it is just A intersection B. Okay, understandable? Okay, let me now ask you a little bit more interesting questions. Okay. The interesting question is, I think this is a good question. I give you two sets. I want you to imagine it. I want you to answer this by imagining it on a Venn diagram. A minus A minus B is equal to this. First imagine it, and then I want to prove it for you using the rules of set algebra. Okay, can you imagine what will be the answer? If they are numbers, what is the answer, by the way? If A and B are numbers, what is the answer? It's just B. If they are numbers, be careful. It's not a good analogy. I just want to emphasize that. Don't think as the sets as numbers. If they are numbers, of course the answer becomes B. But do you think that coincidentally this also becomes B? In general. Of course it might be, sometimes it is equal to B, but is it in general equal to B? So what is it then? No. Yes?
A intersection B.
A intersection B. Yes? Why is that? Because let us try to imagine. This is my A. This is my B. When I say A minus another set, it means that I am interested in all elements in set A which are not in set A minus B. Yes? Is that understandable? That this is the elements of these are the elements within the first set that are not in the second set. Okay, but what is the second set? The second set is A minus B, and if I want to draw them for you, to highlight it, this is here. This one that I am highlighting now is A minus B. Now let us review it again. When I want to highlight the whole combination, I need to look for all those points within the universal set so that those points are within the circle representing A, but not within the colored region. Do you agree? This is the meaning of A minus B. So what is that part left? I am interested in those elements within A which are not in the red region. So do you agree with what is left for me is this one? So this one is my question mark. Yes, but coincidentally this has a name in set theory. What is that? A intersection B. Okay, so you see that Venn diagram is a good idea, but let us try to have a fun a little bit. This is optional, but let us just do it. We want to do it rigorously. So I want to I don't know, is it a good word? It's not a good word. I want to calculate this set expression, set theoretic expression. So I want to do some algebra for you with your help, of course. I told you, this part is optional. Okay, so you help me. If I want to do this, what do you think I will do? When I start from A minus B, I have two subtraction operators, but the priority is the one within the pair of brackets. So what does it mean? It means that I don't even start this one. So I copy and paste, but I want to do something for this one. What do you think I will do? Yes?
convert using the formula.
Yes, I told you that. Usually subtraction is useless in set theory, so let us get rid of it. So it becomes what? A intersection B complement. But if you can go one step ahead, it means you understood everything. So what should I do now? Now I can do the second minus sign. But how? Yes?
It's A intersection everything in the
Yes, yes, yes. And no, everything in the brackets? Complement, yes? So this becomes A intersection with everything in the pair of brackets complement. Yes? But now, which rule is applicable here? Which law? I erased that, the name. De Morgan law. Yes, because I have intersection, but I am interested in its complement. Do you know what was the rule? So I copy and paste the first part. But for this one, De Morgan laws tells one of the De Morgan laws tells me you can complement this, you can complement this, but the price is to change the intersection to union. Is that right? But I can do a little bit better. Copy and paste the first part. Copy and paste here. But what can I write instead of B complement complement? B. And I have union. Okay, does this remind you of a rule? It's distributive. But before doing distributive, if you haven't forgotten, you have to be careful about one exceptional case. That was if a set is repeating itself. If a set is exactly repeating itself, that is, distribution law is useless because it repeats itself. This is absorption law, and the answer becomes the set which is repeating itself. But this is the case? No, I am on the safe side. Do I have really three different sets? Yes, A complement, and B. So as Oscar said, that is exactly distribution law. So I distributed. I distributed it, but you can distribute it for me. So how should I write? A intersection with A complement. Here? A intersection B, but here? What?
Union.
Union. Yes, so I distributed A intersection within, inside the pair of brackets. But this is easy. The overlap between a set and its complement is the empty set, union with this. But the next step, I have a set, I don't know what that is. I am unioning it with the empty set. So what is happening? It is the set itself. And that's exactly what you guessed using the Venn diagram. So the Venn diagram is also a powerful tool, yes? Because at least it was much quicker than this method. But this is the rigorous way of doing it. Yes? Okay, let me also ask you another question. Do you think, now let us concentrate on, I don't know, if we're having a little bit of fun, let us concentrate on operation intersection and subtraction. Okay? Do you think that subtraction is distributive over, no, do you think intersection is distributive over subtraction? Before doing that, I want you to formulate a question for me. My question is that, do you think that this operation is distributive over that operation? Okay, let me go back to the world of numbers because I want to make sure that you understand the question. For the time being, forget about the sets and go back to the world of numbers. Okay? In the numbers, let me answer this immediately. I have an operation multiplication and addition. Do you remember one of them is distributive over the other one? Do you remember? Which one is distributive over the other one? Multiplication is distributive over addition because this formula is correct. Yes? But is addition distributive over multiplication? Okay, but before answering yes or no, you should be able to formulate it for me. How should you formulate if addition is distributive over multiplication? How do you formulate it? You write A plus B times C and ask yourself, is it the case that A plus B times A plus C? Yes? So we know from algebra that this is true, this is false. Okay? Yes? Okay, let me ask you another question. Let me make it with division and addition. Which one is distributive over the other one, if any? To answer this question, we have to formulate first. Okay, so if you say division is distributive, how should you formulate it? You need to write what? You need to read numbers, A, B, and C. I put what here? Division. I put what here? Addition. Okay? And then ask myself, is it the case that what happens? A divided by B, A divided by C, and addition. So, by the way, let me write it in fraction form. Do you think it's true or false? Because if instead of this one, I write the fraction line, this is true or false? This is false. Yes? The other way around is true. Be careful. This is true. This is false, of course. So this means that no, this is not. So this is not distributive over this one. Okay? Okay. Now you understand what is going on. I want to go back to the world of sets and ask you the same question for these operations. Let me keep it. For these operations. For intersection and subtraction. Okay, so let us just ask the question for these operations in the world of sets. For example, let us formulate if it is the case that this one is distributive over that one. How do you write it down to formulate it? You tell me. I need 3 sets. For distributivity, I always need 3 elements of my 3 sets and 2 operations. Okay, then I can formulate the question and then I can answer, is it true or false? So let us see that, how can you formulate it for me? A intersection B minus C. Is it equal to what? A intersection B minus A intersections. So this is the formulation of this question, that if this is the case that intersection is distributive over subtraction. This is just the formulation. It might be true or it might be false. But what is your opinion?
Yes.
You think it is? So then the burden of proof is on you, yes? Okay. If you don't mind, let us first use the Venn diagram to investigate, because it is important, because either we should say this is false. If this is false, my duty is to do what? To bring a counterexample. If this is true, then the proof, I have to prove it rigorously. But because I don't know, I am in a limbo situation here now. Might be that is a good idea if I investigate this using the Venn diagram, which is at the level of your course. Okay? The rigorous one is just for fun and it's optional. But for this one, we can check it. But here I have 3 sets. I have to be a little bit patient. So this is the universal set. The most general case is this case, that all of them have some overlaps. And then I have to copy and paste the same picture once more. Yeah. So let me try to be a little bit careful here. Okay, so let us try to understand what is A intersection B minus C Let us just understand where is B minus C. B minus C are those parts which are within the circle of B but not in the circle of C. Yes? So it is here. This is B minus C. Then I want to find its intersection with the circle, the green area, the overlap between the green region and the circle of A. What is that? This is the circle of A, and this is the green region. I want to find the overlap. Do you agree with me? This is here. So this is exactly A intersection B minus C. But now let us go to this one and then try to understand this. A intersection B is the overlap between A and B. So this is A intersection B. And I don't know how to draw it. The other one is A intersection C. This is A intersection C. But now I am interested in red regions that are not in green regions. What is left is exactly that orange region. Yes? Is that clear? So it seems to be true. At least the first investigation shows that. But now let us try to prove it rigorously. Okay, yes, that is true, but we want to prove it rigorously. So how can I do that? So I start from the left-hand side because this is an identity I want to prove. Exactly like identities, I start from the simple side and try to manipulate it so that I can reach to the other side. Okay, so can you help me? What is the first step? Let me write it in front of your eyes. I want to write something in front of it, yes? So what should I do? What? Yeah. No. Why should I do that? No. I can only do this rule here. So it means that I have to copy and paste this part and then use your rule here. So what should I write now? No, intersection. This one complement. So C complement. Yes? Okay, what can I do now? Can I distribute something? No. Distribution needs 3 sets. I have it. It also needs 2 different operations. But both of them are intersection here.
But strangely, I mean, it's not right, but you can write it as though it were.
No, that is right. But why?
So
the reason is that I can use the idempotent rule. Instead of one single A, I can write A intersection with it A itself, and that is the trick. So what you do, you write A intersection A. Why this is good? Because I saw on the right hand side I have 2 A's. So it motivates me to write in a way that I have 2 A's. And then it's not that hard to see that A can be written as A intersection A. And then I have intersection, the rest. Yes? But now, associativity helps me to regroup them in any way that I like, and commutativity allows me to interchange the places. So, what is beneficial here? I take one of these A's and this B and put them together. I am allowed to do that because I am interchanging, so commutativity, and I am regrouping them, associativity. Okay? And then I can also write intersection, and I take this A with that one. So take your time to understand that everything is really legal. Yes? Yes or no? But it is not going to work. And it's a hard question, actually. So let me see. No, that is not a good idea at all. No, it is harder than this I imagined. Okay, so let me clean it. Because what I have shown is not wrong, but it is not the one that I want. Because what can I do? I can write A intersection B. For this one, I can just write A minus C. What I have shown is correct, but it is not what I want. Okay? So, yes, I realize that is harder than I thought. But anyway, it would be even more fun. Okay? So, this time, I break the rule and I start from the right-hand side. Now, I didn't break the rule, by the way. This is the correct one. So, the first one, I broke the rule and I got stuck. Yes? The rule is start from the more complicated side. Yes, that is the reason. Okay? So, I broke my own rule. But can you help me to write something? So, let me write it in front of you. The first step should be clear for you. What should I do? I get rid of this sign. So what should I write? I repeat the first one. I transform it into intersection. The price that I have to pay is to complement the whole expression. But still, the fun part is starting, yes? So I copy and paste for the time being the first one. And then what can I do here? One of the De Morgan laws, yes? So it becomes intersection, but here I can separately complement them. The price is to you. Okay, then what?
Distribute.
How?
The first set A intersection B.
Exactly. So what you are thinking is taking this in your head to be one set. And then you can distribute. Yes? So then it becomes, let me just ask your help. So I took this in my head to be one set, and then everything is in order. I have 3 sets, all of them are different. One operation is intersection, the other operation is union. Everything is in order, so I can distribute. Yes?
A union, A intersect B,
Yes?
and intersect A complement.
Yes?
And B,
Well, don't get confused.
A intersect B,
Yes?
and intersect C complement.
Exactly. And then?
Intersect union.
Union. Yes?
Yeah.
Yes. Is that right? Yes or no? Okay. Now, what do you think this is? What do you think I will do here? Is it distribution? No, because the signs are the same. So either associativity should be involved, or commutativity, or both. So here I use both. Yes? For example, I commute them and group A and A complement together. Yes? So it becomes B intersection A complement. Okay, take your time. Do you agree that this one and that one are the same? Yes. Okay, what can I do here? What do you think? Is it distribution? No. So I need to probably use associativity and commutativity, but let us have an eye on the left-hand side. It will guide you what to do. So how do you think I will group them? By looking here, it means that B and C should be somehow together and A separate. So I will do the same thing. So I will write A first, B and C together, because all of the operations are intersection. That is not distribution. This is associativity. So far so good. But can you tell me what is this one? This is the empty set. And then B intersection with the empty set is what? The empty set. And the empty set union with this set is the set itself. So it becomes equal to A intersection B intersection C complement. But what can I write instead of B intersection C complement? B minus C, and I am done. So this becomes A intersection B minus C, and that is the left-hand side. So I was able to start from the right-hand side using all these fun algebra and then write to the left-hand side. So that is really proved, yes.
Is there any explanation about precedence if subtraction on this has precedence over unions and intersections?
Is
there any convention that subtraction is over intersections and unions?
No, I don't think we have to put pair of brackets. So if you write something like this, I think it is ambiguous. So you have to prioritize by pair of brackets. Yes. Okay, any questions here? Now let us explore the other way around. Do you think, so this confirms that intersection is distributive over subtraction. But do you think the other way around is also correct? Because for the union intersection pair, both of them were true. But do you think that is also the other way around? Do you think the other way around is also true? Whenever I ask you this question, first you have to formulate it. Okay, so how can you formulate it for me? Is subtraction distributive over intersection? First formulate it for me. So I need 3 sets. So how should I formulate the left side? I have to write minus here, pair of brackets, and then intersection. And then I ask myself, is it the case that, what? What? A minus B, intersection A minus C. This is the formulation of this question. But what is your instinct here? Do you think that this is true or false? Or might be true, might be false, yes? In general, yes, it is false. Yeah, it is not correct. Yes. If it is not correct, you can bring a counterexample. And because usually it shouldn't be hard to bring a counterexample, let us pick things randomly. Yes? Yeah, I don't think, and randomly and simple. Okay, so let me take, I hope that it works, okay? So let me write 1, 2, 3. And let me write B, 1 and 2. Let me write C, I don't know, 2 and 3. Hopefully it works. Yes? Can you tell me in your head what is the left side? First in your head, do the intersection. What is that? 2. And then do the subtraction. 1 and 3. Yes? The right hand side, A subtraction B. What is that one? Yeah, what is that? A minus B is 3. Intersection A minus C is 1. So it is empty, so it works.
Oh no, it's intersection.
Yeah, it is intersection, but that's empty. So it means that, yeah, I mean the counterexample works. That's what I meant, okay? So it means that this is the counterexample for this one. But I will change a little bit. This is not the same question, but I want you to understand that in this case, the true sign is this one. Okay? This one is true, but it has nothing to do with distributivity. Because distributivity only needs a pair of operations on the left and on the right. If I change this to union, it is correct, but it has nothing to do with distributivity. Okay? Is that clear what I'm saying? But let us prove it for fun. Let us prove this. So distributivity was answered here. That was wrong. But let me put union and try to prove it, okay? And I want to wait for you. Yeah, I mean, you should be able, in principle, to be able to do that yourself. Okay, so this is a different story. So prove that A yes. Yeah, if you know. So let me give time a little bit to others as well. Okay. Any ideas? Yes?
So you can, I guess starting from the left-hand side, you can rewrite the subtraction as intersection of
Yes.
the complement.
Yes.
And then De Morgan's law, it's
You can also start from the right-hand side, of course, but then you have to factorize, because factorization and distribution are two sides of a coin, yes?
Yeah.
Okay. But do you agree with me this is De Morgan's law? I mean, so it was very easy to understand that this is indeed the De Morgan law, yes? Why? If you give the role of the universal set to A, that is just the De Morgan's law. Okay? Why? Because if A is the universal set, what is the meaning of this? This is B complement. Union, what is this? C complement. Yes? And then if A is the universal set, what is this one? This is the complement of this set. Yes? So it is B intersection C complement, and that is De Morgan's law. Yes? So this is one way of looking at it. And the other way is actually to prove what you said. So let me start from the right-hand side this time to stick. In this case, what actually Oskar said is also very easy. But let me start from the right-hand side. So what can I write for the right-hand side? I can use this difference rule 2 times. Union. Yes. And now this is distribution, but I want to do it the other way around because I can factorize. We learned that factorization is more the same as distribution, but from one side to one side is called distribution, the other side is factorization. So what is left for me? B complement union, C complement. And then of course I can use De Morgan's law here to write it as B intersection C totally complement. Yes? This is De Morgan's law. But then I have intersection and then complement. So I can write it as A minus B intersection C, and that is the left-hand side. Yes? So that is also easy. Okay, so we can stop here. There's only one part of set theory I want to continue with, and that is a little bit about the cardinality of finite sets. So we can have actually, that will be the last part of the lesson. We have the lesson tomorrow, yes? At 5 as well. No? Ah, you had it on Mondays this week. Okay. Anyway, we will have only one session to finish this chapter and then this section and then go to the next topic. Any questions? Thank you.